All right, this is the last section that will be covered before our upcoming quiz on Thursday. Give you more detail regarding the quiz later this week. I think that it'll start around noon, but whether we'll do it on Mastering Physics or whether you'll just go straight out of Canvas, I'm still working on that right now. But I wanted to make sure that I covered this subject on simple harmonic motion. And so what we're going to be doing then is solving the Schrodinger equation for the simple harmonic oscillator potential. And so this is the subject of section 40.5 in your text. And again, that'll be the last subject covered for the quiz. But in terms of the midterm, which is going to be 2 weeks from Wednesday, we'll also be covering some solutions for the hydrogen atom, and that'll be in chapter 41, and I outlined that for you in the announcements that I sent out last night. Okay, so with a mass on a spring, that mass experiences simple harmonic motion, and so we've already had a section on that in Physics 208A, and so there's always a restoring force. We have a force that's proportional to the displacement of the mass away from the equilibrium position. So if we have and let's make this mass be on a level surface. Here's your unstretched length of the spring. If you pull that spring a certain distance x from the equilibrium position here, x equals 0, then there'll always be a restoring force F that's equal to minus kx. And so that's our Hooke's law relationship. And we've done a lot of things with this in Physics 208A where we plotted up the force versus the displacement for a mass spring system. Now, using the Schrodinger equation, what we're more interested in is not the force, but the potential energy function. And so the potential energy, you may recall, for a mass on a spring is equal to 1/2 kx squared. And so we can get then the force, our familiar force relationship, by just differentiating the potential energy function with respect to x. So that's minus d by dx of 1/2 kx squared, or minus kx. So what we have then with the simple harmonic oscillator potential is a parabolic function in x. And so that then is inserted into the Schrodinger equation, minus h bar squared over 2m, second derivative of psi, and this will be a one-dimensional motion problem still, so it's just with respect to x, plus our one-dimensional harmonic oscillator potential, 1/2 kx squared equals e psi. And so our goal here then is to solve this equation for psi. So that's minus h bar squared over 2m d squared psi dx squared, plus now u is 1/2 kx squared times psi equals e psi. Okay, so this is a nonlinear second order partial differential equation. And because it's nonlinear, it's not as easy to solve as the problems we've looked at so far. The problems we looked at so far, this was a constant step potential, which could then be incorporated over into the e, and then we could get something that looked like e to the minus I kx for our functions before. But now, let's look up at the data projector, and we see what the solutions are in terms of what are called Hermite polynomials. And so we have different allowed solutions. This is psi 0 of x. It's equal to this normalization factor times e to the minus alpha x squared over 2. And the psi 1 of x is going to be an x times e to the minus ax squared. And so what you end up with then, as you go to higher and higher n values, which are allowed solutions to the Schrodinger equation, is some polynomial function of x multiplied by e to the minus alpha x squared over 2. And so these then become your allowed solutions. Now this actual solution to this equation can be verified by taking each one of those values, taking the second derivative of it with respect to x, and then plugging it in with the harmonic oscillator potential equaling 1/2 kx squared. And you can show that the left-hand side of this equation equals the right-hand side, provided that E of n, this is the solution for the nth energy state, is equal to n plus 1/2 times Planck's constant times the frequency. Or, because Planck's constant times the frequency is equal to Planck's constant over 2 pi times 2 pi frequency, we can also write this as h bar omega. So Planck's constant times the frequency is also h bar omega. And so E1 then, that would be, or excuse me, E0, because what n would equal 0, that would be our 0-point energy for the simple harmonic oscillator. That would be when n equals 0. That would equal 1/2 h bar omega, or 1/2 Planck's constant times the frequency. And so what we find then is that this value is called the 0-point energy for the simple harmonic oscillator. Which means that even if this mass is still and there's no vibration in it at all, it still has a minute amount of energy of oscillation that is associated with what we call the 0-point energy for this system. So this exists even at absolute zero, when there's no molecular motion to allow for any object to move at all. Classically, quantum mechanically, there's still a 0-point energy that is associated with virtual particles randomly colliding with this mass and giving it an average energy that is on the order of 1/2 h bar omega. And so this is essentially then a way of saying that the mass spring system has restless leg syndrome, and you can't settle it completely down to no motion at all, because if it had no motion at all, that would violate the uncertainty principle. Then you'd know exactly where it was, and so that means you'd have an uncertainty in the momentum, because delta p delta x is equal to h bar. And so if you knew exactly where it was because it wasn't moving, then that means its uncertainty in momentum would force it to move. So the uncertainty principle prevents this mass spring system from having zero motion, even at absolute zero. Okay, and so then we go up to higher energy states. This would be E1. So this then would be equal to 1 plus 1/2 h bar omega, or 3/2 h bar omega. E2 would be 2 plus 1/2, or 5/2 h bar omega. E3 would be 7/2 h bar omega. And each time that we elevate the energy by one value of the quantum number, we get a discrete energy that can exist, but nothing can exist in between. So as we would think from a classical point of view, that as this system vibrates back and forth smoothly, and then energy starts leaving the system, that it would smoothly have an energy that would make a transition to zero. That's what we would think. But instead, what's happening is that this thing is going to vibrate, at a certain value, a certain amplitude, and then suddenly, at the same frequency, it'll go to a lower amplitude, and then suddenly to a lower amplitude, and then suddenly to a still lower amplitude, but not occupy any of the amplitudes in between, so that it will make this jump from one energy state to the next, which is discontinuous, just like with the hydrogen atom. As the electron jumps from one state to another, you give off a certain burst of energy in the form of, say, a photon. Now, what kind of energy would the harmonic oscillator give off? Well, interestingly enough, E of n plus 1 minus En is going to be just here, n plus 1 half h bar omega minus n plus 1 half h bar omega. And so the only thing that's left then is an h bar omega. The n plus 1 halves h bar omegas are going to cancel. So we just get h bar omega, or Planck's constant times the frequency. So what is that? That's the energy of a photon that is vibrating, that is equal in frequency to the vibration rate of the simple harmonic oscillator. So a photon then can be released. When we make a transition from n plus 1 to n, it can give off that energy in the form of a photon. And then it can give off the energy in the form of another photon that's equal to Planck's constant times the frequency. So that all of these delta E's are Planck's constant times the frequency. All the way down to E naught. And so once it gets down to E naught, then it's at its most stable state. And at that point, it will still be vibrating, but it will no longer have the tendency to want to go to a lower energy state. Just like an electron in the ground state of the hydrogen atom is not going to want to go to a lower energy state. That is the bottom energy that it can have. And it's not going to spiral into the nucleus as we would think classically. And similarly here, you're not going to have something that's going to continuously lose its energy until it has zero motion. Quantum mechanics requires a zero-point energy, and it requires that the energy jumps are discrete jumps that have an increment that's equal to Planck's constant times the frequency. And so if we think of everything as being kind of similar in a way, in terms of you can be in one energy state or another, but they're discontinuous, then you can imagine that we're all just kind of like cartoon creatures. Because in a cartoon, what you do is you take a bunch of frames, and if the frames are close enough together, you have the illusion of the continuity of motion. Whereas in a quantum mechanical system, you start looking at the individual frames, and you see that you're going from one frame to another, to another, to another, but the frames are so closely similar to each other that the eye doesn't pick up the discrete nature of it. And in a cartoon, you'd have to pull out a few of those frames to see that discontinuous motion. Well, how would you pull a few frames out of this picture? Well, you could go to a universe where Planck's constant is a much larger value than the value that it is in this universe. And in that kind of a situation, then you might have me going from here to there, and discontinuously jumping from one energy state to another, which I'm doing anyway, but you just can't see it because the frames are so closely packed together.